Good day. So welcome to this another session. So I have here this another presentation and I adapted this PowerPoint presentation by James Walker. So in this session we'll be talking about the concepts of application of Newton's laws. So what are the things that we'll be talking in this presentation? Okay, so we'll be talking about the frictional forces, strings and springs. So the forces involved in this system, then translational equilibrium, then objects, the forces involved in connected objects, and of course circular motion and its application. Okay, so first we are going to have frictional forces. So friction is basically indispensable in our daily life. Everywhere we can find friction. But though friction is always involved in our daily activities, there are things or there are systems that we have to consider the elimination of frictional forces. So friction exists whenever there is surface interaction. Okay, so and basically when we talk about friction as a force, this is always opposite to the direction of motion. For example, if you're going to move a chair on east direction, basically you're going to apply force to do that. And according to, say, the laws of physics, since there is surface interaction, there is friction. As you move a chair, as you apply force in order to move the chair to east direction, the frictional force is going to west direction. Okay, so it is always opposite the direction of motion. That is why whenever you are going to remove the force applied on the chair, the chair will basically stop at some time. It's because of the opposing force, which what we call as friction. Okay, so basically for the surfaces which are basically rough, we can say that there's a full friction. Okay, whenever the surface is smooth, of course the friction is lesser. Okay, so there are two types of frictions that we have, basically, although there's a lot. But in this presentation, we basically deal with kinetic friction and the static friction. Okay, so friction again is being experienced whenever the surfaces are in contact. So say there's sliding forces, surfaces, or interacting surface in general. The basic formula for friction is, we have this. So F is equal to mu times the normal force N. Okay, so you have there. But for the specific friction that we'll be talking about, this presentation, we have to specify through the use of subscripts. So for the kinetic friction, we're going to use the subscript K. So you have there Fk is equal to mu K times N. So the mu refers to the coefficient of friction. So for mu K, of course, it is specific for coefficient of kinetic friction. And for the static frictional force, of course, that should be S. So Fs is equal to mu S times N. So normal force, basically, we have had that one already in the previous presentations I had. Okay, so frictional forces on different objects. Since you have there the mu K, then as a constant, okay, so that constant specifically refers to material. Of course, different material have different coefficient of friction. So you have here a typical coefficient of friction between the interacting surfaces. So you have here the rubber and concrete. So you have there the static friction and the kinetic friction. So you have steel on steel, glass on glass, and so on. Okay, so notice that as the frictional force existing between the interacting surfaces is lesser, then the coefficient of friction is also less or lower in value. Okay, so we may generalize that those surfaces that are basically rough will be having higher coefficient of friction. Okay, so frictional force. How do we determine the frictional forces? Okay, so we may determine the frictional forces using or through experimental method. Okay, so we use basically spring balance. So you have here in this figure, so spring balance is being used to determine the kinetic of kinetic frictional force. Okay, so for you to determine the kinetic frictional force, you must take note the application of force. Okay, basically it is equal to the force applied on the object. This is actually the force. This one, this force here and this one are basically equal. When can we say that they are equal? Whenever the object is not accelerating or the object has what we call as constant velocity. And based on experimental results, kinetic frictional force is independent on the surfaces, but this is basically dependent on the weight of the object, as you can see in the figure. So as the weight of the object increases, the frictional force also increases. This is basically the force required to move the object at constant velocity. And since um, uh, the velocity is constant, then the summation of all forces is equal to 0. And basically, we may say that this force here, this one, is equivalent to this force because of the condition that forces acting on the system is equal to 0. Okay, so you have had that one in the previous videos prepared. Okay, in the concept of statics. Okay, so on the other hand, when we talk about frictional forces, uh, this is actually the force that enables the object to stay at rest. Okay, so if you're going to apply force in a box and the box is not moving yet, then we may say that the force you applied is basically equivalent to the frictional force. But if you're going to consider the amount of force that will enable the object about to move, well, that's basically the maximum static frictional force. Okay? And it is actually shown in here. Okay, but when the object now is moving with a constant velocity, then that is what we call as kinetic frictional force. Okay, so you have here in this illustration, you notice that the object is of course at rest, and in this second figure, you apply the force, yet the object is not moving, meaning to say that the coefficient, the frictional force existing on surface and the object is equal to the force you applied. And in here, you increase the amount of force, but still the object is not moving, then we may deduce that the frictional force is still equal to that. However, in this figure, you applied now the maximum force that enables the object about to move, and that is basically the maximum static frictional force. Okay, so in this figure here, you have here the range of the frictional force. So you have basically the maximum frictional force, which is static. Okay, and this one here, this is the maximum amount of frictional force or force that you're going to apply so that the object will start to move. Okay, so you have there the equation for the static friction. And basically, it is also independent on the area in contact with the surface. Okay, but again, the frictional force or the static friction is dependent on the weight. Notice that in the previous, I remember that in previous discussions that we have, the normal force is related with the weight. Okay, so forces that exist in strings and springs. Okay, so we have here what we call as tensional forces, because strings basically related, or rope basically related to what we call as the tensional force. Okay, so if you're going to pull the rope this direction as presented in the figure, then you are applying. Okay, so there is the tensional force existing in the rope, and this rope is basically increasing. Okay, so you have here. Okay, okay, so you have here. So if you're going to talk about, let's have another, which is basically not talking about tensional forces. Let's talk about the compressive forces. Say if you're going to apply, so let me have my photo in here. So I'm just going to remove my face. So if you're going to imagine, say, a block of wood, if you're going to press that one, you are going to compress that one, then the block of wood is actually experiencing another force, and we call that one as compressive forces, a force, I mean. Okay, so the direction of tensional force and compressive force is basically different, because in this illustration the tension should be away from each other. Okay, if you are going to pull the rope away from each other, okay, while compressive force, you have to press it, so the forces applied on is basically going to towards each other. So in this illustration you have here the tensional force, of course. Okay, so basically the tensional force denoted in these different variables that we have are basically equal. Okay, so in problems that we are going to deal with, we have to simplify the problems. Okay, we have to simplify the problems. How do we simplify that? So we consider the rope to be massless, because we know that in real sense, the rope will contribute. The different point actually of the rope has different tensional forces because of the contributory effect of the mass. So if you're going to consider the mass of the rope, then we have to use differential calculus for us to determine the change of tensional forces at different points of the rope. But to simplify the problem, we have to consider the rope to be massless. So in here, you have here the rope, and of course the tensional forces is existing, of course, is acting on the rope. Okay, so in this figure, this is actually another illustration. So you have here this pulley. So they are actually connected with each other. So you have here the box, and you have here the person pulling the rope up, downwards. So in effect to that, according to the third law of Newton, this box here will go upward because you are applying a force. And you have here the existing force, the tensional force found in the rope, that is trying to counterbalance the force of the weight that is going downward. Okay, so you have there. Then for the springs, we call this one as spring force. Okay, so for strings, we may consider that one as tensional force, but for spring, we have this spring forces in springs. Okay, so different springs have different spring forces. Okay, so these spring forces are actually quantified using this equation, and we call this equation as Hooke's law. Okay, so if we were going to talk about restoring force, then you must have the negative sign before the K. The K there denotes the spring constant, meaning to say that different springs have different constants. Okay, so you have there. So in further, discussions that we will be having, we are going to delve more on this spring force, particularly in problem solving. Okay, so you have here the force actually that can be found in springs can also be considered as spring force. So the spring force, sometimes it is denoted as F sub S, is proportional to the displacement, meaning to say as the displacement of a spring increases from its normal it will increase, then the restoring force or the spring force is basically also increasing. Okay, if you are going to graph that one, basically that is proportional with each other. So if you have here the F, then you have here the S, I mean the X, or vice versa. So you have here. So, but in spring, this is what we call as the limit, wherein at this point, this is what we call as the breaking point. So that breaking point there, so the spring is basically under stress and it will not return into its original form, meaning to say you have reached the critical force applied. Okay, so for translational equilibrium, so when we talk about equilibrium, okay, the idea of equilibrium is very important in the analysis of systems which are static in nature or not moving, or should I say non-accelerating system. Okay, so when we talk about equilibrium, you should not delimit yourself to the system which are not moving. The system can also be moving and at the same time in the state of equilibrium whenever the velocity is constant. Okay, because in the previous discussions that we have, particularly on this law of Newton, the system, if the system is how do you call this one? The velocity is constant, meaning to say that the net force acting on the system is equal to 0. Okay, so whenever the net force acting on the system is equal to 0, then that must be in the state of equilibrium. And you have here in this equation, the sum of all forces is equal to 0. Okay, so this one, in the problem solving that we are going to have in the next presentations, which involve problem solvings, okay, so we are going to apply this one. And this one basically is considered to be the first condition of equilibrium. Okay, so first condition of equilibrium. Again, this is, I'm going to give you a scenario. So you have here the building. So if the building, okay, so you can never find a building which is moving basically. So that building is under the state of equilibrium, or we call it one as translational equilibrium. Why translation? What is the difference? What is the other type of equilibrium? Well, we have this rotational equilibrium, wherein in the rotational equilibrium we'll be talking about torque. The summation of torques is equal to 0, and we consider that one as the second condition of equilibrium. That is second condition of equilibrium. But for the sake of this presentation, we are going to have first a translation equilibrium. But in presentations, in problem solving, we are going to delve with this too. Okay? So you have here the translational equilibrium. So you have here this picture. This is the physical picture that we have. Now, this is what we call the free body diagrams that we have. So again, in the free body diagram, you have to take into account all the forces that is being involved in the system. So you have here the weight of this, how do you call this one? Pail with water. You have here the force, weight, and of course the tensional force. Tensional forces, because there's a lot of ropes existing in this system actually. So you have here, and then you're going to superimpose that one in the Cartesian coordinate system. So you have here, this is another free body diagram referring particularly to this system you have there. So I hope you follow my the arrows that I used to specify what particular system is being represented in the free body diagram. While this free body diagram here refers to the system that can be found in the pulley. where the pulley can be found, basically. Okay, so you have there. Then there are objects just like with this. So you have here the connection. So the system is connected with a rope, but there are other systems, like, aside from this pulley system, wherein they are connected. For example, you have here these masses, blocks, okay, mass 1 and mass 2. They're actually connected with a rope. And if you're going to apply force on this system, of course, because of the tensional force, because of the rope that connects between these two objects, this will accelerate. So this will accelerate. If you're going to consider this force, then the acceleration will be to this direction. Okay, so if you're going to find actually the acceleration, how much acceleration this system have, then you have to apply the second law of Newton. That is, the summation of forces is equal to ma. But in this case, mind you, in this case, you have to individualize this system. You are going to apply the second law of Newton in this system 2 and system 1. So that's the way how you analyze that one, and you will find that one during our presentation for problem solving applications. Okay, so these two here, the tensional forces, basically is the link between these two. So it gives you the link for you to find the acceleration. Okay, so you have there. So this is what I have told you a while ago. So you are going to individualize the system, meaning to say that you have to put the system in, you have to create a free body diagram for each system. So this is for system 1 and system 2, then create an equation that will be talking about this one. So if that problem will tell you that there should be a frictional force, then you have to consider frictional forces acting on the system. Okay, so in the system, if we're going to look at it, it is quite complicated, though complicated. But if you're going to look into the system, if you're going to understand and apply the second law and individualize this system, isolate this system, then analyze it, then everything would be easy. Okay, so in this system, you have here system 1, system 2. So this system 1 basically can be superimposed in the Cartesian coordinate system, and you will have the forces acting both in along y and x-axis. So along x-axis, you have tensional force. If there is a friction acting on it, then you may include that one, which is along x-axis. But for y-axis, you have there the weight of the object and of course the normal force. But for system 2, there is no x-axis forces. Okay, what are the forces involved basically for system 2 in this system? So you have only the weight of the hanging mass and of course the tensional force. Okay, and you are going to superimpose that one along y-axis only. Then in this case also, it's very important for you to note of the direction of the acceleration. You have to assume. Anyways, in problem solving, you will know as to whether the assumed direction is correct or not based on the sign given. Okay, so you have here, in this case, it is assumed that the object will move downwards in the system 2, and in effect to that, according to the third law of Newton, the system 1 will have to move in, will accelerate towards positive direction. Okay, so that's it. Then for circular motion, the circular motion is also involved. Can be also another application of the laws of Newton is the circular motion. So basically, the figure tells you that the motion of the object along in the circular path is uniform. So you have here uniform circular motion. So whenever the object is in the state of uniform circular motion, the magnitude of the velocity is constant. Only the direction keeps on changing. Or should I say, the speed is constant. The speed doesn't change. Okay, if that's the case, then the force that holds the object in the circular path is constant. And we call that one as Fc, or the centripetal force. The force that is directed towards the center of the circular path is called as centripetal force. Okay, that is basically the force that holds the object, okay, in the circular path. So you have here this equation. Basically, the term v squared over r is actually your acceleration. That is centripetal acceleration. So v squared over r. Okay, that is a centripetal acceleration, or the acceleration towards the center. That centripetal acceleration exists only solely whenever the system is under circular motion. I mean, the object moving in a circular path is in uniform circular motion. Okay, so you have there, substitute that one to, then you have here, you come up with the equation, which is basically this one. Okay, or we may write the equation as, for the centripetal force acceleration, as Fc is equal to mv squared over r. So you have there. Okay, so the circular motion, the force involved in circular motion actually be applied in a real sense. Say, for example, you have here this road. If this road is basically flat, not banked, that is where there should be banking of the curb. This one, if the road is not banked, of course, this vehicle would most likely to slip off away from the road if the speed is at critical, or the speed of the vehicle is quite high, or say, how do you call that one? Okay, it will slip off from the road. So in order for that one to happen, you have to bank or to tilt the curve. So you have, this is a bank curve. So notice that the forces acting on the system is basically maximized. So you have here the normal force. So basically increases the traction between the tires and the road to avoid slippage. Okay, so you have here, this is the application of the forces in circular motion. So we are going to apply that one in our problem solving in the future, in the next presentations that we are going to have. Okay, so if the system is under a state of non-uniform circular motion, we call it as NCM, or non-uniform circular motion, the acceleration basically can be decomposed into two. So you have here the tangential acceleration and the centripetal acceleration. So with that, the component or the resultant acceleration will be going to this direction as presented in the figure. So you have here. Okay, so when can we experience this kind of acceleration, or the this centripetal acceleration and the tangential acceleration? So that is, we can experience that one whenever the speed is changing. Okay, so the speed is not constant, just like in the roller coaster. Okay, so the speed in the roller coaster basically is changing. So that's where you can find this type of accelerations in circular paths. Okay, so in summary, we have here the friction. Basically, there are two types. So you have kinetic friction and static friction. Then for the forces in the spring, we have the tensional force. And for the spring, we have here the restoring force, or the spring force. Okay, so for the objects in translational equilibrium, it is basically an interesting part. Okay, so the summation of forces acting on the system should be equal to 0. And please take note that it is not necessary that the system should be at rest, because there are systems that is moving, but the net force is equal to 0. So that should have a constant velocity system. Okay. So circular path, where the object is following, we have there the circular motion. And the force that holds the object in the circular path is the centripetal force. And of course, it is associated with the centripetal acceleration. Okay, so that is for this session. Then in the next session that we are going to have, we are going to delve more on problem solving. Okay, thank you for watching.